Welcome to Module 5, Part 1. This is continuation of what we started at Module 5, Part 0, where we introduced what is a gas mixture and the rudiments of a perfect gas mixture model. We'll continue with this development and further develop the PG mixture model. We'll also quickly make up a problem, solve it manually, and verify using test code. So let's say we have a gas mixture. The mass is sum of partial masses. Mole is sum of partial moles. And as you recall, the molar mass of the mixture is given by mass over mole of the mixture. So we would like to figure out, suppose we know the pressure and temperature of the mixture, suppose P and T are given. We would like to know how to find properties such as enthalpy, entropy, etc. of a gas mixture. That's our task. So the first thing to understand how a mixture behaves is through superposition. Let me just explain. So suppose we have a mixture made of, let's say, some red molecules and black molecules. Dalton models essentially says that if you have a situation like this, you can treat the mixture as if they share, as if it's a superposition of two pure systems with red molecules in one and black molecules in another. In other words, here's the mixture. And here we have mk kilomole of species 1. We can call it, say, m1 kilomole of species 1 and n1 kilomole of species 1, whereas m2 and n2 are the numbers here for the second type of component. Of course, we can generalize this for any number of components. So the first model for a gas mixture comes from Dalton, and here's the Dalton's model. It says that all the molecules share the same pressure, same volume, and temperature by each component. Let's understand that first. Obviously, if I have a container and I have a gas mixture, each component has the same volume as the container. So the room you're sitting right now, the volume of the room is geometrically defined. And so if I say, what is the volume of nitrogen in the room? That's same as the volume of oxygen. That's kind of obvious. So how about the temperature? Recall what is temperature of a gas. The temperature is average. Temperature can be thought of as is a reflection of the average kinetic energy of molecules. So obviously, temperature at a point, when we say temperature at a point is 300 Kelvin, what do you mean by that? A point in a system will still have billions and billions, trillions and trillions of molecules. Molecules are so small. So given that a point has so many molecules, you can easily find an average kinetic energy. In case of solid, it's the vibrational kinetic energy that reflects the temperature. And in case of a gas, it is the translational kinetic energy that reflects the temperature at a point. So if you have red molecules and black molecules, they cannot have different temperatures. They must have the same average kinetic energy because the molecules will collide with each other and make sure they don't have two different temperatures. So that's kind of one way to understand why there is nothing called the partial temperature, so to speak, is same for all species and same as the temperature of the mixture. But now how about, so therefore it is same pressure. On the other hand, what is pressure? Pressure is the force per unit area. As you can understand, it is how molecules are getting, the way molecules bounce off a wall. So imagine the force per unit area will depend on the momentum exchange. The change of momentum as the molecules collide a wall and comes out will determine the amount of force. Suppose in a classroom, some students are having a red ball in their hand, some with black balls, and we're all throwing into the wall. So obviously, the pressure would be what? The force per unit area created because of this momentum exchange. Essentially, that's exactly what's going on in a gas. The molecules are bombarding a wall, and as a result, there's a momentum exchange at the wall causing the pressure. Well, we don't feel the pressure right now because the forces on our skin is balanced by the forces of the molecules from the other side of the skin, so we are kind of in a balance. But as you go, say, you dive into a pool, go to the bottom of the pool, you can feel the pressure because the surrounding pressure is higher and you can start feeling it. Similarly, if you go up in a mountain, you can feel the pressure change in your ear. So obviously, pressure depends on the number of collisions as well as the velocity. So the number of collisions, if we suddenly take all the black molecules away from a mixture of black and red molecules, you can understand that the pressure will be lower. So what Dalton's model says is that the pressure is made of contribution pk, called the partial pressure, of each component. So let's draw this system again. So we have these black molecules and red molecules. We have them to mkg, n kilomole, V is the volume, and T is the temperature, and P is the pressure. Well, according to Dalton, we can, sorry, my diagram doesn't look exactly identical, but you understand it's the same volume, same system. And here we have only black molecules, and here we have only the red molecules. And what Dalton says basically is that in this superposition, we have mk kg of a component, nk kilomole of a component, and the volume is the same for each component. Temperature is the same for each component. However, the pressure is different from each component. So everything else is same. So this will have mk, nk, and pk. So as you superpose these two simple pure gases, we get the mixture. Also, the mixture, in case of when you treat the mixture as a mixture of ideal gases, according to Dalton, the mixture will follow the ideal gas equation PV equals nRT, and each component will follow its own ideal gas equation, where volume and temperature are the same, but the pressure is different, equal to partial pressure of the gas. Also notice, because, okay, let's write down these two equations again. For the mixture, the ideal gas equation of state is valid, where P is total pressure, or the pressure of the mixture, V is the volume, N is the mole, R bar is the universal gas constant, and T is the temperature. And for a component K, P gets replaced by its partial pressure, N gets replaced by the mole of component K. So these are both ideal gas equation of state. One applies to a component and one applies to the mixture. So if we summing equation 2, we get summation of pKV the volume is not dependent on components, we can take it out. Similarly, R bar and T are constant as far as components are concerned. And we end up with V times summation of, and now we know this is nothing but the total mole of each component add up to N. And if we using equation 1, nRT equals PV. Therefore, summation of pK is P, a very important relation. In other words, the partial pressure of all components add up to the total pressure. Also, if we divide equation 2 by 1, we get another important relationship. That the partial pressure to the total pressure is simply the mole fraction of component K. We'll soon see the importance of partial pressure in air conditioning when we discuss air conditioning in the future module. But for the time being, notice this, the simple formula, this plus summation of pK equals P, is easy to remember, and it's easy to express properties of a mixture when we understand the partial pressure of individual species. One more way of expressing a mixture is think of a mixture made up of partial volumes. In other words, suppose we have a mixture where the black molecules and the red molecules. So this is another picture of the same mixture, and this is known as the Amagad model. So suppose the mixture is divided in a manner that we have on both sides we have the same pressure and temperature, but a partial volume Vk. So then again we can write for the mixture PV equals nRT, and for the partial volumes PVK equals nKRT. Why this kind of description is also important, and this is known as Amagad's model as opposed to Dalton's model. It becomes important because this is a simple way of creating a mixture. While Dalton's model is very nice to express a mixture, existing mixture, you can think like it is existing mixture is a superposition of partial, superposition of pure gases with their own partial pressures. Amagad's model is useful because suppose you are trying to build a mixture at a pressure P, temperature T, then you find its components and mix them with their partial volume Vk. So you get Vk amount of component K and mix them together, and then you'll end up with a mixture that you want. And as you can see, if I divide the two, we get Vk over V equals Nk over N equals Yk. So this formula can be generalized because then we can write Pk over P equals Vk over V equals Yk, which is Nk over N. So what is partial volume? As you can see, summing it up, partial volume can be written as mole fraction times volume. So therefore, sum of the partial volumes equals the total volume, because summation of Yk is 1. So Amagad's model, which we are not going to use as much as Dalton's model, essentially is a counterpart of the Dalton's model on volume basis. Here we have a mixture. You can imagine, suppose in your room we have oxygen and nitrogen mixture. You can imagine, oh, I can separate oxygen and nitrogen. How much volume the oxygen will occupy? The answer would be simply the Vk, which is the total volume of your room, times the mole fraction of oxygen, which is, we showed in our previous part that mole fraction of oxygen in air is about 0.21. So if you have a 100 meter cube room, the volume of oxygen, partial volume of oxygen will be 21 meter cube. On the other hand, if you go by Dalton's model, you have a 100 meter cube room and 100 kPa is the total pressure. What is the partial pressure of oxygen in that case? It will be 21 kPa. So this is a simple way of looking at a mixture. Finally, we'd like to evaluate some properties of mixture. Okay, so in general, we'll express a mixture, mkg of a mixture, which is mk kg of k, and it will have a mixture as a volume V, temperature T, and partial pressure Pk. So of course, the total mass of the mixture is given by the sum of its component masses. Total mole is given by partial moles of its components. Total pressure is given by summation of Pk. And now suppose we want to calculate what is the internal energy U of this mixture. It will be summation of the partial internal energies of the mixture, which is mk times uk. Uk is the internal energy of the component k. So we are just summing up, again, the superposition principle here. And this you can write, if you want, the total mass m times xk is the mk, and uk, which is m times summation of. So it's like a mass fraction weighted internal energy of individual species. So for the PG mixture model, if you use the perfect gas formula, recall that for PG model, for a species, delta UK will be what? CV times CV of component K times temperature difference, right? Delta T. CV times delta T. CV of component K. So this is the same formula as delta U equals CV times delta T from your PG model. Go to table J to brush up or chapter 3, where PG model is discussed. So this we already know for a pure component. So therefore, for a mixture, what happens? For a mixture, delta U will be delta capital U over M, which is delta of these quantities, which is summation of delta UK, which becomes summation of, if we substitute delta UK from here, CVK xk times delta T. And delta T is same for each component, so we can write that as delta T times summation of xk times CVK. And notice what this is. This is mass fraction weighted CVs of each component, which is the mixture CV times delta T. So as you can see, the formula for delta U for a mixture is just the same that we remember for a pure component, except CV has to be evaluated by mass fraction average, weighted average. In other words, if I have a mixture made of hydrogen and nitrogen, I got to know what is the mass fraction of hydrogen and nitrogen in the mixture, and just recalculate the CV, and all our formula for CV will be applicable. Well, just for completeness, we can write the formulas for delta H for a mixture will be M here is small h, Cp times delta T, whereas Cp is mass fraction weighted Cp of each component. Likewise, if you go for a entropy, on the other hand, is a function of pressure and temperature. We know delta S is given by Cp ln T2 over T1. That's for a pure PG model. If you go back to the PG model, you can find formula for change of entropy. But as you can see, because now entropy is a function of pressure, and in a mixture for a given component, you have to think of the partial pressure. So that's why the entropy of a component will depend on the partial pressure of the component, as in addition to its temperature. So for a pure component K, delta Sk is given by Cp of K. Again, temperature is the same for every component, Rk ln P P2 of K, P1 of species K. These are the partial pressure, and Rk, as you can recall, is R bar over molar mass of K. So now that we know how to figure out entropy change, we already know how to find entropy change of a pure substance, but if it's in a mixture, all we do is the pressures are replaced with their partial pressure of each component for a given component. So for a mixture, then it becomes delta S is summation of, it's again mass fraction weighted entropy, and you can just manipulate these to show it will turn into Cp of the mixture ln T2 over T1 minus R ln P2 over P1, where and R Okay, let's solve a quick problem. Let's have a mixture, a chamber with, let's say, we have 1 kg of nitrogen, 1 kg of oxygen, and 1 kg of water vapor in a chamber. It's given that the pressure is 100 kPa. Find the vapor pressure, partial pressure of water in the mixture, which is also known as find the vapor pressure. Okay, so we know the partial masses of the mixture, so we can find the mole fraction, we can find the, so we know from the pH2 over P must be YK, YH2O I mean here. So therefore, we have to find the mole fraction of water vapor. That'd be our first step. So again, we could use the formula or derive everything from scratch. We know N of H2O is going to be equal to mass of H2O, which is 1 kg, divided by molar mass of H2O, which is 18, 1 over 18 kilomole. Likewise, we can find N of nitrogen, which will be 1 over 28, and N of oxygen to be 1 over 32 kilomole. And this gives us YH2O to be NH2O divided by, we sum all the partial mole, and that can be shown to be 0.45, about 0.45. So this is the mole fraction of water vapor, and since the total pressure is 100 kPa, so therefore P of H2O is simply 45 kPa. So we found the partial pressure of water vapor. Now this is an interesting thermodynamic question. Now suppose we ask, what must be the minimum temperature so that the water vapor is in a gaseous phase, or at least vapor? Well, that's where Dalton comes handy. Look, the water vapor has a pressure of 45 kPa inside this chamber. We can forget about nitrogen and oxygen because they all exist independently. So we have a certain volume, a tank of water. Inside the pressure is 45 kPa, and we know that it's in gaseous phase. It's vapor, superheated vapor. So the temperature should be at least above the boiling temperature at 45 kPa. And what is the boiling temperature at 45 kPa? If we, I thought I had a tab where, okay, let's start, go to the property tables, and if we go to the pressure saturation table of water, and at 45 kPa, you see the temperature is somewhere close to 80 degrees Celsius. So we can say the temperature must be was it 70, what did we say, at 45, say about 80 degrees Celsius, must be greater than 80 degrees Celsius for this to be true. To verify that using test calc, we can launch the PG model or NPG model, because you have more than 2 components, and launch the PG test calc and compose our mixture. We have 1 kg of oxygen, 1 kg of nitrogen, and 1 kg of H2O. Now that we know the pressure, which is given as 100 kPa, notice that all the partial pressures are computed and displayed here. So, sorry, I lost that screen. So the answer is 45 kPa is verified.